In this example, we're told we have water with a given specific volume flowing from a reservoir through a turbine. It's operating at steady state. The inlet and exit diameters of the pipe are equal, and we're asked to determine the maximum power output with a given flow rate. And some information is given in the picture as well. So if we were going to find the maximum flow rate, what we're going to do is assume that the flow through the system's internally reversible, and we're also going to assume that the water is incompressible. So we'll go back to our Bernoulli's equation that we derived in lecture 32 and write out the power out. This will be the maximum over m dot. That's going to be the same as the power out for the internally reversible case, right? And if you go back to the notes, you'll see that that will equal the following for the incompressible case. Okay, so just a reminder, the assumptions that go into this form of Bernoulli's equation are that we're assuming a steady state conditions, an internally reversible flow, one inlet and one outlet, and in addition, for this particular form, we're also assuming that the fluid is incompressible. One thing I should also point out is this is actually being applied to a control volume. The control volume looks like this. It's following the pipe and going around the turbine. And there was another example I did for this lecture, and I didn't draw the control volume. I should have. But that's the control volume that we're using here. All right. Since the inlet and exit diameters are equal, what that means, and the fluid is incompressible, it means that the velocities at the inlet and outlet will be the same. So this will be 0. Since this comes from conservation of mass. From conservation of mass, rho VA1 will equal rho VA2 for steady flow. The mass flow rate in equals the mass flow rate out. If the diameters are same, the areas are the same. If it's incompressible, the densities will be the same, and then you're left with V1 equals V2. All right. Well, so we can then simplify this just a little bit. I'll get rid of the negative sign by flipping the terms. So it'll be V times P1 minus 2 plus, you know what, I realize I made a mistake. Up here, these should not have been plus, these should have been negatives. Apologize for that. So then when I flip the negative sign here for the potential energy term, it'll be Z1 minus Z2. All right. Now we just simply need to plug in the data that we're given. So the specific volume is given as 0.001 cubic meters per kilogram. So let's just write that down. That corresponds to, just by the way, a density of 1,000 kilograms per cubic meter. It's an easy number to remember. It's used all the time in engineering. P1 is 1.5 bar. That's the pressure right at the inlet here. It's a little higher than what you have at the outlet. You see the outlet, it's at 1 bar. That's exposed to the atmosphere, which is roughly at 1 bar. The P1 is higher because it's under water, and so the pressure will go up. You'll recall at the very beginning of the course we talked about hydrostatic pressure, and that's why the pressure at 1 is a little bit larger. So the pressure at 2 is 1 bar. We need to convert these over to pascals, so this will be 150,000 Pascal, and then 1 bar is 100,000 Pascal. That's just for the unit conversions. G, of course, is 9.81 meters per second squared. Z1, if we put our coordinate system right here, pointing upward, again, G is pointing downward, then Z1 is equal to H1, which is 160 meters. And Z2, you'll see, is equal to minus H2. Z2 will be equal to minus H2, which is 10 meters, minus 10 meters. All right, the last thing that we're given is the mass flow rate was 950 kilograms per second. So we can plug the numbers in to get the power. The maximum power out would then end up being 1.63 megawatts. This will be the maximum power you can get. The actual power will be less because a real system would have some irreversibilities to it. All right, that's all there is for this example.